Hi, good morning, everyone. I'm Astrid Van Giffen. I'm one of the conservators here at CMOG. I'd like to welcome everyone on behalf of myself and Leanne Iwasato, who is our other conservator and my co-moderator today. I'm very excited about this panel because we get to talk about one of my favorite glassy subjects, deterioration. Not only are the effects of deterioration beautiful, as we will see in the images from our panelists, but the fact that it deteriorates at all is one of the most surprising and coolest things I know about glass. We generally think of glass as a chemically inert material. Yes, it breaks, but as long as we can keep the baseballs out of the windows and the cats off the shelves, it will be around forever. But that's not the case. Glass is constantly changing. Although in most cases, these changes are imperceptible to the naked eye and gradual enough that chances are that the glass will break before the changes are noticed. But if you look carefully, you can find signs of deterioration around your house. Do your drinking glasses have a faint iridescence or haziness from going through the dishwasher for the last 10 years? Do those wine glasses that have been sitting in your wooden cabinet feel slimy and smell funny? And my personal favorite are the little tiny white crystals in your double paned windows. These are all symptoms of glass deterioration. And the thing that causes these changes is water, something we often think of as harmless. When I talk about glass deterioration, I'm referring to chemical changes in glass. And I find it useful to think about three types of deterioration based on the circumstances in which they occur. The first is glass that has deteriorated during burial, so in the ground, like archaeological glasses. The second is glass that has deteriorated outside, like stained glass windows. And the third is glass that has deteriorated in an indoor environment. And this is what I call atmospheric deterioration. In all these cases, water, either in liquid form or as moisture in the air, is the main culprit. As you can imagine, deterioration in an indoor environment can be very problematic for museums. And this type of deterioration is the starting point for our discussion today. Guus Verhaar will give us more details in a minute, but I would like to start us off with a quick introduction. The examples of deterioration that you might find around your house that I mentioned may seem relatively minor, but these are just the beginning. As the deterioration process continues, glass starts cracking, losing surface, and eventually falls apart. This contradiction of something that we think of as inert, namely glass, being so strongly affected by something as ubiquitous and unassuming as water is fascinating to me. But not all glass is created equal. We talk about glass as if it is a single material, but there are seemingly endless combinations of elements that can be added to silica to produce glass, something glass makers can take advantage of to form glasses with the properties they want. The composition of a glass determines its working properties, like the melting temperature and how much it can stretch without reheating, as well as the properties of glass once it's cooled, like how easy it is to engrave and its weight and clarity. It also determines how it reacts with its environment, or in other words, how fast it deteriorates. The deterioration process is gradual for most of the glass in your house, because it is likely a very stable soda-lime composition. But there are unstable glasses that deteriorate much faster. Historically, these types of unstable glasses tend to come from periods and places where glassmakers were experimenting with compositions, like Venetian glass of the 16th and 17th century, 17th century English lead glasses, and the glass from the American studio glass movement of the 1960s and 70s. One of the most shocking examples I've seen personally is a piece in the Corning collection that was made in 1970 and is now basically turned to dust. The title for this panel is Change Over Time, and that refers to the changes that happen to glass, but also to how we think and talk about the deterioration of glass. There are many different terms to describe glass deterioration, and they have changed over time. But there's no standard set of vocabulary, even within conservation. Similar terms don't always mean the same thing in different fields of study. Many of the terms used to describe this type of deterioration in conservation are based on symptoms that are visible like weeping, which is the formation of droplets on the surface of glass that happens in the early stages of deterioration, or crizzling, which describes the network of cracks that form as the deterioration progresses. In conservation science, there is talk of alteration layers and corrosion, which some people don't like because of its association with metal corrosion, which is very different from glass deterioration. The term sick glass, which some of you might be familiar with, has been used for a long time, but I prefer to avoid it because it implies that this phenomenon is contagious or curable. I call glasses prone to this type of deterioration unstable because their compositions make them more chemically reactive than other glasses. And my preferred term for the process is atmospheric deterioration of glass, because atmospheric moisture is the key factor. But this term is not ideal either, because one, is a mouthful, and I often revert to saying crizzling in conversations, and because atmosphere is not limited to indoor environments, which can lead to confusion. So to expand the stories of glass deterioration, we have brought together a conservation scientist, a conservator, a scientist working in industry, and an artist, because they each deal with changes in glass, but in their own way and with different goals, ranging from trying to understand the deterioration process to predict and identify it, to the practical aspects of how to preserve objects that are reacting with their environment, to finding new applications for glass that intentionally degrades, to exploring the visual changes and what those changes mean. I'm really excited to see where this conversation will lead. We're going to start off with some short presentations by each of the panelists, followed by a hopefully lively discussion, which will be led by Leanne. So to start us off, I would like to introduce Guus Verhaar. So Guus is going to be giving his point of view, but also a more in-depth introduction of deterioration. Guus Verhaar is a postdoctoral researcher at the Delft University of Technology in the Netherlands. He is currently working on the non-destructive characterization of ancient glass objects with the purpose of determining the provenance, elucidating production techniques, and assessing the condition of objects. To achieve this, he is using a suite of non-destructive techniques like neutron and X-ray computed tomography, neutron activation analysis, and X-ray fluorescence. Previously, he held a position as a researcher for a joint project between the Rijksmuseum, the Corning Museum of Glass, and the University of Texas at Dallas, in which he worked on the characterization of degraded glass samples in order to better understand fundamental degradation processes within the glass and how they affect the formation of degradation products on the surface of unstable glass objects. Guus holds a PhD from the University of Amsterdam on the topic of historic glass degradation. The main goal of his PhD was the development of a non-invasive early warning system for the identification of unstable glass in museum collections using ion chromatography. In addition, so take it away, Guus.
Thanks, Astrid. Thanks for this really work. I wrote it myself, so it's quite a wordy biography with a lot of technical terms. So in this very brief presentation, I will skip that bit and try to explain to you very briefly what the degradation of glass in museum collections looks like and why it is a problem we have to deal with. And Astrid already mentioned some key points, which will now be illustrated by some visuals. So it will be very brief and just the tip of the iceberg, but I hope you end up with an idea of why we consider this degradation of glass, of the material, so important for the conservation of the artworks. Next slide, please. Yeah, as Astrid mentioned, there are basically three main groups of glass, historic glass that we can distinguish. On the left, you see a vessel glass, so a bowl from the Corning Museum of Glass. In the middle, stained glass windows, which is glass that is exposed to the atmosphere by purpose. So the vessel glasses are usually for indoor use. And then the third group, which is also, I think, well, I don't know if it's the largest, but it's a very large group of archaeological glasses. And each type of glass has their own degradation process. So there should be some animations here. So if you go to the next click, we might, yeah. So we see the degradation occurring on this object, where it changed from being transparent to almost completely opaque and a much more matte appearance. Yes, next click, please. For stained glass, the typical degradation process is the formation of what's often referred to as corrosion crusts because of the exposure to harmful pollutants, for example, in the atmosphere. And the next click. The third group, archaeological glass that has been buried in the ground for such a long period that the degradation has occurred mainly in the ground. And if it's excavated, the glass is in pretty stable condition usually. But what has happened is that a thick layer of laminated glass structures has formed on the surface of the glass, which leads to this characteristic appearance as, and what they refer to as irisation, so a rainbow effect. Next slide, or next click, yeah, thank you. So, but in this talk, and this has been the main topic of my research for the past 10 years, is the degradation of vessel glass objects in museum collections. And it also relates to flat glass, which is kept in museums. But I will focus this presentation mainly on the three-dimensional vessel glasses. Next slide, please. Yeah, so, and this is where I've shifted to. I've added this little rectangle to show you what I'm working on now. But we'll skip that for today. Okay, next slide. And just to show you some examples of what it might look like, this is actually a study object, which is which was kindly donated to me by a colleague at the Rijksmuseum, Margot van Schinkel, who had this object in her cupboard, her kitchen cabinets, but she didn't use it. It's an Irish coffee glass, but she never used it. And suddenly, when she was cleaning out the kitchen or something, she found these objects, and what struck her was something that she was very familiar with, namely the accumulation of moisture on the surface of a glass. And this is one of the main degradation patterns we observe in museum collections, is that glass that deteriorates accumulates moisture on the surface. And as Astrid mentioned, this is a problem because water is the main culprit for degradation. So that might accelerate the degradation. Okay, next slide. Next click, yeah. And what this moisture actually is the dissolved salts. So these are, what actually happened is that salts have formed on the surface and attracted moisture from the atmosphere. So that when glass dehydrates, these salts crystallize when the glass is kept in a dry environment. And you can actually see the crystals forming on the surface of the glass. So that's also a typical example of a sign of degradation, is the formation of crystalline material on the surface. Okay, next slide, please. And you have seen this ball, but this glass has been moved, and I don't know if I get the order right, but it moved from one location to another where the humidity of the glass was slightly lower in the final destination. So what happened is that if you click now, you'll see an animation, and you can even see more clearly what has happened to the object, where it turned from pristine condition apparently to degraded very heavily, what we refer to as crizzling, which is the formation of a network of cracks on the surface. But at the time of the change of location of the object, it wasn't clear that this object was susceptible to show this behavior. Next slide, or next click. Yep. This is another example of crizzling. And when this object was made, it was completely transparent, but also colorless. So the crizzling is the formation of the cracks, also led to the also enabled the penetration of oxygen into the glass network, which caused the change in oxidation state of manganese. So that means that manganese was added to decolor the glass originally, but when it changes oxidation state, the manganese itself turns pink. So that's what happened all over the surface of this object. And I will come back later to this object and also demonstrate why it's important that we deal with these kind of issues. Next, please. And I think this is the final example. This is an enamel plaque from the Rijksmuseum collection. And enamel, as you probably know, is glass fused on a metal substrate. But that glass can also deteriorate and attract moisture to the surface. In fact, this will be, sorry, I just got a message from Rob that he has to leave for a minute, but I hope he returns safely. So what happened is that the dissolved salts interact with the moisture and the metal to form these very peculiar corrosion products, which you only find in this, where the combination of these materials, so glass that's deteriorating and metal present. That's when these corrosion products form, and they are very exotic and quite beautiful, some might say. So these are all examples of advanced stages of degradation, but in order to understand what is going on, we need to take a step back and look at the basic chemistry of glass. So next slide, please. Glass is generally considered to be a combination of three main ingredients, to which other elements can be added to create color, for example. But typically it's three ingredients: a network former, a network modifier, and a network stabilizer. The network former is the main, sort of the backbone of the glass network, chemically speaking, and it consists of silicon dioxide, and the raw material used is quartz, so sand. But in order to work with this, to melt it, you would need to achieve a very high temperature, and the glass makers in the past weren't able to do that, so they started adding other ingredients to the network, like network modifiers in the form of soda or potash, which changes the glass structure and lowers the melting temperature so that they could actually make a glass melt. But that changes the glass network, and it makes it less chemically stable. So that's a problem. So in order to counteract that, they added a stabilizer, which is often lime, and results in the presence of calcium oxide in the glass, and this stabilizes the network. Okay, next slide, please. And what was already known in the past is that the ratio in which these elements are added determines if a glass is stable or unstable. So the main factor determining glass stability and its tendency to degrade is the composition of the glass itself. And a very telling example is are the glasses produced by George Ravenscroft in the UK in the 17th century, where he actually made a patent for for a specific glass production process. But 2 years after he filed the patent, he added something to his patent saying that he had changed the recipe because his glasses would start to crizzle and spoil, basically meaning that they were degrading in this very short time scale even. And those are some objects that we now see as problematic, which are very heavily degraded. So the early Ravenscroft glasses are often problematic in museum collections. Okay, next slide, please. So this is one of the two technical slides in my presentation, but just to show you what is going on inside the glass during degradation. So we have on the left is the simplified structure of glass where the silicon and oxygen form the backbone. So that's the black dots and the open white dots. And in between are cations. And these cations are added as the network modifiers. And they are somewhat mobile within the glass network, meaning that they can also be extracted from the glass network. So when glass undergoes an interaction with water, this is what's happening. So the glass structure changes. These cations are replaced by even smaller cations. And this is accompanied by the migration of molecular water into the glass, resulting in what you see on the right, in an altered surface layer, where these cations are depleted. It has a lower density and is rich in water, so it's quite responsible to the environment in which the glass is kept. And this is an important feature because initially it may not look like the glass has changed, but when you change the environment, for example, when it's stored in a dry environment, the water that is incorporated in this layer may evaporate, causing a shrinkage of the top layer, resulting in the crack formation. Okay, next slide, please. And an important aspect is that these cations, for example, potassium in this case, K+, move out of the glass network and are deposited on the surface, where they can react with atmospheric molecules. And these are the salts you have already seen in the previous slides. Next slide, please. So during my research, what we wanted to do was based on a question from a conservator. Can we actually identify unstable glass before it shows these signs of degradation? So the idea we had was, if we can identify the presence of these ions which have leached out of the glass, even though they are not visible, we may be able to identify unstable glasses, because not all glasses will show this behavior. It basically depends on their composition. And then when they are put in an unfavorable environment, the degradation will occur. And this slide just demonstrates you that we went to the Museum Boijmans van Beuningen, where they had just done a large collection survey, and they identified glasses which they considered stable and unstable, and cleaned them all at the same time. So we had a baseline level of the condition and appearance of the object. And after a certain amount of time, we started analyzing those sample deposits using ion chromatography, of which you see a faint image here on the left. And we were able to identify that for the unstable group, so the darker gray bars, we do see elevated concentration of these ions on the surface, even though you don't see any very clear moisture accumulation on the surface. So that was an interesting outcome, and that sort of gives confidence that we could identify these unstable glasses in an early stage. Next slide, please. This is also an animated slide. So the research we were doing with the ion chromatography also gave some insight into conservation treatments. This object was in the Rijksmuseum collection, and it appeared matte all over, and being quite a modern glass, so early 20th century, modern compared to the 16th and 17th pieces that were in the museum collection. We wondered if this was intentional or not. But with ion chromatography, we were able to actually sample a little bit of the surface deposits. And it turned out that this was quite easily removable. So if you go to the next slide now, we can see the difference here, where ion chromatography analysis showed that this matte appearance was actually the result of moisture accumulation again. In this case, specifically as a result of sodium formate, salt, which is quite hygroscopic, so it tracks water quickly, and it dissolves in water. So the cleaning procedure was fairly easy to remove all the salts, remove the water that might damage the glass even further. And now it looks like this again. Next slide, please. And another important thing to realize is that even though people have said this looks pretty beautiful, it it might, but it's very dangerous for the object because it may alter the structural integrity of the object. Because this little pot used to have a lid, but that completely disintegrated because of this crizzling process, and we can already see a crack forming here near the handle. So I'm a bit worried about this object, how long it will survive, even though it's kept fairly stable in the museum conservation studios. It is quite dangerous because the structural integrity also degrades during the chemical degradation. And then finally, in the next slide, I can show you what that this is really a surface phenomenon, because at the cross section of the glass where it broke, we can already see the formation of new cracks. But what we see most is that the surface layer, which is the edge between the green background and the glass itself, you can actually see that there's a quite sharp distinction between the degraded zone and the unaltered bulk glass. And this also brings me to sort of a conclusive remark. When we're looking at change over time, the glass we are looking at in museum collections has already passed the ages. So a lot of the degradation processes have already occurred. And what we do to them now might influence what the glass looks like, but the active degradation is less of a problem than how we deal with the objects. And I think that's a good enough introduction, I hope, for now. And maybe we can go to the next panelist.
Thank you, Huus and Astrid, for that great introduction to glass deterioration. I'm Leanne, and I have the distinct pleasure of introducing the rest of our panelists. So let's start with Bodil. Bodil Lemaine works as a glass and ceramics conservator at the Conservation Studio of the Rijksmuseum in Amsterdam. In this department, she is responsible for the conservation and research on the museum's collection of glass, ceramics, and stone objects. This also includes hands-on conservation and making recommendations for handling, storage, display, and movement of the collection. In 2008-2009, she was involved in a large conditions survey of the glass collection in conjunction with the relocation of the glass collection to the then new storage facilities for a major renovation of the museum. The condition survey revealed that approximately 10% of the vessel glass collection displayed changes of appearance, ranging from surface haze to advanced crizzling. This realization led to questions and concerns for the collection and set in motion the beginning of a long-term research project on the issue of glass degradation. Her current research projects include technical research on terracotta artifacts from the sculpture artist Quellinus, and Bodil also runs a private conservation studio in the center of Amsterdam. Well, please take it away, Bodil.
Yay. Sorry, I had to unmute myself. That's quite key. Well, I already had welcome to this part of the seminar. We go immediately to the next slide. Please. Yeah. Just to show you where I'm from the Rijksmuseum in Amsterdam. You see that in the middle to the left is our conservation studio. Next slide, please. Yeah, again, our conservation studio on the outside and the inside, just to illustrate or introduce myself, who I am. Well, in this short presentation, I like to tell in rough lines something about the history of our glass collection and its documentation, and how the documentation or lack of documentation led to a condition survey on a part of the collection. And I finally like to tell you what this survey set in motion in the end. Next slide, please. So in the Rijksmuseum, amongst other things, we take care of the museum collection of vessel glass that contains around, well, over 1,500 objects from a period that runs from around 1500 to the 20th century. Now the glass collection, and a large part of the other collection is stored at CCNL in Amersfoort. That's our new storage facility, which you see here on the left above. And on the right, you see the storage cabinets. Next slide, please. An important part of the collection include a large collection of Venetian glasses and Façon Venetian glasses. Can the next slide be there, please? Yeah, thank you. Dutch diamond engraved glasses and wheel engraved Dutch and German glasses. And this is an example of the glass that's on display in the museum at this moment. But as with almost all historical collection, our vessel glass objects have stood in many different places in their lives. Of course, we have provenance of a lot of objects, but that doesn't really tell us where the objects exactly have been. And also within the Rijksmuseum, the glasses have had many different places, both in exhibition, internal and external, and in storage spaces. And I'd like to show you some examples. So the next slide. Yeah, you see an example of an early example of picture of 1927, where you see it shows an arrangement of glass in wooden showcases. And behind it, you see the window where direct light and sunlight is falls into the room. And the next slide, please. Oh, yeah. Oh, where is it? Yeah. Again, two examples, one of 1946, and this is again glasses in a wooden cabinet built in the wall. And on the left, on the right, you see again a cabinet standing again in direct sunlight. So the glass is really beautiful and pretty in the sun, but not really preferable for the glass. Next slide. Yeah, on the left you see one of the first display cabinets made of metal and glass, and this was in 1962. But on the right side you see an example of one of the old storage cabinets made of wood. We had a lot of different cabinets, and the storage was on different places in the old museum building with no real climate control at that point. Next slide, please. And here you see one of the storage from 1994. And though these cabinets were improved, that were made of metal and glass, but it was still in one of the towers of the museum. And on the right, that's between 1994 and 2003. This is the open study collection storage facility in the museum. So, yeah, and the next slide. Yeah, and the museum didn't have a ceramic or glass conservator until the mid-50s. It changed at that point, but it was not before the middle of the 1980s that for the first time a conservator was employed who took care of the glass collection specifically. Especially from the early periods, we lack a lot of information around the condition and whereabouts of the objects. And in the archive, sometimes sporadic information is found about a glass object from the collection, like you see on this inventory card from 1909. On this card, it's mentioned that this glass is suffering from decomposition disease, but this was not a standard. So sometimes we find these, but it was not a standard. A structural overview or database of the collection was lacking of this vessel glass collection. And even normal general condition reports were not available of all objects. From the 80s, this improved step by step onwards, but then it stayed a long-term wish to check and clean the entire glass collection in order to create a condition baseline. So we could have a reference point to build on from that moment onwards. But to tackle that structurally, in the midst of daily busy museum life with objects on display and on loan, that was not easy. Next slide, please. Yeah, so because of the big refurbishment of the Rijksmuseum that started around 2003, almost a complete glass collection was moved to the then new storage facility in Lelystad, in the middle of the Netherlands, where the glass were stored in stable metal cabinets in a stable climate. This unique moment with almost the entire collection together in a new storage seemed like an ultimate opportunity to carry out a collection-wide condition survey to create our much desired condition baseline. Next slide, please. We started the survey with the core collection, which maintained around 400 objects of vessel class. It was supposed to be a general condition survey to create a condition baseline. So the condition in its totality was checked. So aside from degradation symptoms, also chips, breaks, and restorations, etc., were put in the survey. The glasses, we categorized the glasses in 5 categories according to their condition and stability, where A was mint condition and E was general bad condition. On the slide, you see in very short terms the elements for degradation that was mentioned within this survey. After this survey, it was supposed to be that the objects were supposed to be cleaned and stored. Next slide, please. But however, the outcome of the survey showed us that even within this core collection, there was a considerable amount of objects that showed signs and symptoms we could not clearly determine because they were unclear or fake and sometimes only be seen under raking light, and even then were hard to determine what it was that was seen. And like this example, well, this is made under raking light. The glasses looked, a lot of the glasses looked somewhat dusty. Sometimes this was dry, sometimes it seemed a bit damp, but it was very light. And the next slide is another example of this. It's a sort of haze or cloudiness. And sometimes we found a droplet, but it was not standard. It was mainly unclear what we saw. It was unclear what the symptoms were and what was seen. Was it a change of the glass or was it caused by soiling of the surface because it was standing in not ideal display or a not ideal storage situation? Or was it a symptom of degradation problem? Had the climate or the moving played a part in it? Or treatment or cleaning in the past? We didn't know if it was the first time this occurred with these objects. Was it plainly something that was always been there but was overlooked before or not given the attention it needed? Or maybe it was just simply cleaned off in the past without proper documentation. Next slide, please. But another very important question arose as well for us, because what did these fake symptoms meant for us as conservators? How should we act on it? And in a very, very small nutshell, this was the point that set in motion a study and later research where the Rijksmuseum has been involved in during roughly the past 12 years. A study into glass with then the focus on the early stages of degradation processes, where the initial main goal for us was to find a method to recognize and determine the initial very early phases of glass degradation. But it became a research journey of its own, and Guus Verhaar just told you more about that research. But for us as conservators, it became also a process that gave us along the line a lot of insights to different aspects around glass as a material itself and around the degradation processes of glass, a lot of which we sort of knew, but we started to think of again in a new light and new perspective. And we came to think again about glass as a material with a very large amount of varieties in composition, in the making process, and mainly also in stability. Next slide, please. And well, the research by Guus, but also follow-up researches that were a follow-up survey that was done in the Rijksmuseum to create a better condition baseline. It was done in documented in word and image and performed by Margot van Schenkel and Roosmarijn van Beemen, but also in other museum performed by Mandy Slager. Brought us already many insight, but it also gave us so many new questions. Well, some of the questions were new, but some of the questions were old questions or questions of which we thought we had more or less the answer to, but still seem to have a lot of uncertainties around them, like what is the best method to detect early stages of glass degradation? If removable degradation residue is found, should we clean the glass or not? And if so, which method is best for the cleaning of the glass with specific degradation symptoms? And what are the long-term effects of it? And in what climate and conditions should the objects with different symptoms and different stages of degradation be kept? Or do different symptoms mean different approaches in cleaning or storing or displaying and in conservation in general? Can these objects still go on display? Are there time limitations for that? Can they still travel for loans, or should they be kept forever in storage? Can we maybe make a better prediction of the effect of short-term unpreferable conditions that sometimes go along with loans? And what is the best way to document different degradation symptoms seen on glass? That's also a very, very big question for us. How should we classify these symptoms so that comparisons within collection can be made more easily? And what is the best way to monitor these objects? And how can we detect, capture, and document small changes in the degradation process? And how can you make it reproducible so it could be used as a reference during monitoring? Well, these and more are all things we like to know and be able to answer in the future and act on as a conservator. So therefore, our aim is to try from our side to keep the research of glass active and alive and relevant to our profession in order to grow knowledge and preserve collections. So that was it. Thank you.
Thank you, Bodil. A really great introduction to the museum side, conservation side of things. What a great project, and certainly many more questions, I'm sure. So to open a little bit out of the museum conservation realm, we're going to move to Robert Schout next. Rob is a research fellow in the Science and Technology Division at Corning Incorporated. In this role, he brings material science expertise to understand problems with glass pharmaceutical packaging, identify new materials to address these problems, and to describe these advances to pharmaceutical manufacturers and regulatory agencies. Robert earned his BS in ceramic engineering and glass science from Alfred University in 2002, and his PhD in material science and engineering from the Pennsylvania State University in 2008. He specializes in the study of chemical and physical properties of glass surfaces. Since joining Corning in 2008, Robert has conducted research in glass ceramics, Gorilla glasses, and borosilicate and aluminosilicate glasses for pharmaceutical packaging. He is the co-inventor of Valor Glass and has authored 14 peer-reviewed articles, 2 book chapters, 115 technical reports, and more than 100 patent applications. Robert has been granted 66 patents and is a member of the American Ceramic Society and the Parenteral Drug Association. Excited to hear you speak, Rob. Take it away.
Thanks, Leanne. We can go to the next slide. Thank you for that introduction. I feel a little bit out of my element here as a glass scientist and more on the commercial side. But as I listen to Use and Bodil, I think our approach to understanding corrosion and deterioration here, there's a lot of similarities. So I hope I can bring something to the table and hope I get lots of good questions here as we go into the panel. So as a material scientist, we always look at the relationships between the bulk glass composition and the properties that we can observe. And as we think about that relationship, we will also think about the structure of the glass on an atomic scale, and any artifacts that the processing, taking something from the molten state and getting it into the final formed state, and how that processing might have influenced the composition, structure, and finally the properties that we can observe. And in particular, when we think about deterioration, or as scientists more commonly use corrosion and weathering, we really need to focus on what's going on in those outermost layers of glass, so the several microns of the glass surface, and relate those responses to the chemistry of that region. So my key function at Corning is to come up with new glass compositions that are designed for these applications. So both going from very durable to very non-durable. So what I thought I would do is give you a couple examples of that range of the spectrum, but then also tell you about why the surface chemistry is so important in those applications. Next slide, please. So in my graduate work at Penn State, I focused on fiberglass, and this is kind of the epitome of high surface area materials, where the forming process, where you're drawing these into these 10 micron or so fibers, can alter the surface chemistry, either bringing some additional boron to the surface or actually, in some cases, depleting it. What we're able to show is that that level of boron and the structure that it takes at the near surface can introduce new adsorption sites. And what that means is that it's going to change the bonding of that material with the environment that it gets put in contact with. And if you're trying to do corrosion studies on this, it's going to be linked to that concentration and structure in the outermost micron or so of material. So some interesting work there, and it really highlighted for me that boron can move around at surfaces. Next slide, please. So after I joined Corning, we had an opportunity to work on pharmaceutical glasses. And when you think about the objective here of trying to preserve a pharmaceutical solution for years, you really think about trying to drive the durability of that glass to as good as it can be, right? As little deterioration as possible. But at the same rate, the pharmaceutical companies are constantly evolving in what they're making and what they want to store in glass. So the challenge of anticipating the interactions between a new drug product and a glass surface can be very challenging. In the upper right, you can see the evolution of glass packaging over the last 150 years or so, from hand blown and formed from simple soda lime type glasses to the current borosilicates that are used in the industry today. And now we've even introduced boron-free glasses for the same application. And part of the reason that Corning got involved was that there's a long-standing defect here called delamination, that it really came to be when the industry shift from manual forming or kind of flame working or blowing to more machine forming on a turret type machine, where you're going from tube to the vial shape. And specifically what you're looking at in the image in the lower right are flakes of the glass surface that are spalling off and could have entered the drug product. And so being able to understand the origins of this defect and then coming up with a way to address it and prevent it from happening was key. Next slide, please. So that's some of the development that we would do on the high durability side, but we're also interested in very non-durable glasses. So there's an emerging area of bioactive glasses where we're actually engineering the bulk glass chemistry to dissolve rapidly in human body fluids. And specifically what's happening here is that high surface area, almost cotton candy looking glass fibers can be put in the body. And as they degrade, they give off nutrients that basically help regenerate either soft tissue in the case of skin and the photos shown here, or if it's implanted in the human body, it can help with hard tissue regrowth. So in other words, teeth or bones. And depending upon what you're trying to regenerate, you will alter the bulk glass chemistry in order to provide those right nutrients. And unlike many of the silicates that we're talking about, because of the good chemical durability attributes in those glasses. These are really focused on borate or borophosphate glasses, where they're going to degrade much more rapidly. You can see the time scale in the lower left of the order of days, right? Days and weeks that you can completely dissolve these glass materials. Next slide. So I'll come back to this example of pharmaceutical packaging and the role of surface chemistry in this defect. So delamination actually spurred a conversation that I had with a glass artist more than 15 years ago, where Jim Burns out of Pennsylvania, he was a scientific glass blower and was also in the art side of the house. And he introduced me to something called bloom. I'm sure you as an industry know this better than I do. And it became very interesting to me. Well, as I came to Corning and we had pharmaceutical customers reaching out, talking about this defect called delamination, I was reminded of bloom in the artistic sense. And what's happening here is the volatilization of boron and sodium during this tube to vial converting process leads to changes in glass surface chemistry. So that blue coloration is actually a stain that we did to the vial surface, showing how non-uniform that boron can be after that converting process. And it's that region where it's been incorporated that generates flakes. And those flakes are rather large. You can see hundreds of microns, and they're very thin. So only a few microns, or in some cases less than a micron thick. So they are able to be drawn up into a needle and dosed as part of a pharmaceutical product. But of course, that's undesirable because it can have human health effects. Next slide, please. So, and if you can click, this video should play. This phenomena is really obvious whenever we melt and form these glasses. So borosilicate glasses are known to evaporate sodium and boron. All of that material that you see leaving the surface is sodium and boron. And every time you stretch that surface or reheat it, there's going to be more material evolved from the surface. Next slide, please. And so this just shows you during that tube to vial converting process, the glass is heated and cooled and heated and cooled several times, giving many opportunities for that evaporation and condensation process to occur. And as a result, the surface chemistry on the inside of that glass that would eventually be put in contact with the drug product is heavily or significantly different from where we started. Go ahead on the next slide. And so we could image this with electron microscopy, and far away from the evaporating source on the right-hand side of the image here, you can see these deposits, these little spheres of sodium borate compound that have deposited during that forming process. On the left-hand side, you can see where it was heated and where that material evolved from. There's almost no evidence that occurred. But between those, the glass temperature was just right, where material was depositing, but it was also being reheated enough where it was actually starting to melt back into the surface. And it's that region where these defects are most likely to occur. So if you've ever seen bloom and then reheated the piece to kind of get rid of it, what you're doing is reincorporating that sodium and boron into the surface and basically enriching and changing the glass chemistry significantly. Next slide, please. And so we can use tools like dynamic SIMS, secondary ion mass spectroscopy, to look at how that surface chemistry is altered. So the solid lines here show that region of the heel where sodium and boron, the purple and the green lines here, have been greatly enriched in the outermost, say, 100 nanometers or 150 nanometers of surface. That's like 1,000th the width of a human hair. And it's that enrichment that causes those flakes that I showed in the previous slide. So controlling the glass surface chemistry on this scale of hundreds of nanometers is necessary in order to prevent those defects from occurring. So Corning did this through creation of a new glass composition that didn't include boron. And by omitting boron from the formulation, we were able to stop this evaporation and condensation reaction from occurring. Next slide. But in those regions where the boron is greatly enriched, this is where we see really degraded durability. That heel region, you can see here, gives off a lot of extra sodium and boron in standard corrosion tests. Next slide. And that's visible in terms of surface roughness. So again, with an electron microscope, we can see pitting and features. Now, those features aren't a representation of the bulk glass chemistry. Those are an artifact of this forming process. And so those are only hundreds of nanometers or microns deep, and a result of this evaporation and condensation process. Next slide. So as a summary, when we go to look at corrosion and weathering, we can influence that from a bulk glass chemistry perspective, making things very durable, or intentionally designing them to be non-durable depending upon the application. But as we look at defects, they're very commonly related to the surface chemistry and the processing that the glass article has seen. So I really look forward to the conversation here on how art and technology can intersect, and look forward to the panel discussion. Thank you.
Thank you, Rob. That was really, really interesting. And thank you for nuancing our understanding of surface and the formation process. I am going to introduce David next. So David Schnuckel is an artist who works with and thinks through glass at the intersection of finesse and failure. His work exhibits internationally and belongs in the permanent collection of the Glazenhuis in Lommel, Belgium, Glasmuseum Ebeltoft of Ebeltoft, Denmark, and the Museum of American Glass in Millville, New Jersey. He has taught at Alfred University, the Toyama City Institute of Glass Art, Pilchuck Glass School, Penland School of Craft, Haystack Mountain School of Crafts, and the studio at the Corning Museum of Glass. As a writer, he maintains a blog that examines elements of his making and teaching practice called David Schnuckel Uses His Words, and is a regular contributor to Gas News, the newsletter of the Glass Art Society. Schnuckel is currently assistant professor of glass in the School for American Crafts at Rochester Institute of Technology in Rochester, New York. Welcome, David. Go ahead.
Thank you so much for having me. So happy to be part of this group. Let's begin. Next slide, please. So to start, I have a few three very small chapters, and we'll begin with the sort of basic background stuff. Who am I? What am I doing here? Next slide. I am an artist who works with glass. I am also an educator in the glass program of the Rochester Institute of Technology, which is based in Rochester, New York. It's only about 90 minutes or so north of Corning. And I've been there as part of the faculty now for a while. I've been there since 2010. Next slide, please. I've had a relationship with glass for a little over 22 years now. And although I'm familiar with most glass processes, the hot shop and blowing glass, these images that you're kind of seeing on this slide, is a sort of example of what my bread and butter is, not only as teacher, but also as maker. Next slide. And as a maker, I'm predominantly a vessel maker. So I'm seeing a lot of vessels today, which is really exciting. And I've been using the traditions and the theories and the histories and even the politics of vessel making, not only involving glass, but even non-glass instances, as a sort of vehicle for ideas that straddle a line between control and chance. The vessel is really just a formal motif to kind of explore bigger questions and curiosities that I'll illustrate a little later on today. But I have a current sort of focal point on stemware. Next slide. The work that I do as in relation to glass and glass blowing and vessel making is really in service of what I've been calling a pursuit of masterful wrongness. And so it's not really necessarily, I don't claim to know it all, but I'm really interested in research and generating work that sort of kind of accumulates skill and knows the rules of glassworking so well that perhaps the idea of purposefully abandoning it or like deviating from it or even ignoring those rules in various ways can sort of set up or unpack some kind of artful moment or artful gesture. And these are just a few kind of ways in which I do that. That also sort of begins to extend into areas of drawing and print and writing and photo and video. Next slide. I think this is the last one of this chapter, and I wanted to use it as just a sort of platform to talk about, as Leanne had mentioned in my intro, my work and my research really lives at this intersection of finesse and failure. Those are my spirit animals. And so my work is really wanting to pursue some kind of discovery, to discover or find something meaningful within mishap. And so I'm not only thinking about failure within process to take advantage of, but also failure in material conditions too, which seems pretty spot on with today's conversation. Next slide. So I want to talk a little bit about my relationship with this term glass deterioration. And then I also want to cover in a small way how it's a question of how do artists deal with it. Next slide. But I think the question is actually better asked is how can artists deal with it? Matters of purpose, matters of intention. And that's kind of how I'm going to start to kind of approach that subject today. Next slide. This fall, I'm bringing this philosophy that's kind of governing all the things I do in studio. I'm bringing it into the classroom. I'm bringing it into my teaching in a way that I'm really excited about. At this moment, this semester, I actually have designed and I'm leading this seminar studio course on failure to advance students in the glass program at RIT. And we are thinking of it in all kinds of glass and non-glass talking points. Next slide. And so these are the sort of sub-themes that we're navigating through lectures and readings, but also through like discussions and writing and studio projects and field trips. But we're also going to apply this to materiality as well. Next slide. So the one super relevant way that this failure course that I've designed relates to today's panel is how students and we're thinking about and tinkering with, we're about to begin this actual, this sort of next step of the semester is thinking about ways in which glass as a material fails. And we're looking at glass deterioration in a broad way. We're thinking of that term in a broad way. We're thinking about ways in which our making processes worsen a glass body over time in one way or another. But then to also think about ways in which we could make use of it somehow. Next slide. So there's a list making exercise of quote unquote glass wrongness that I had us begin the semester with a little assignment that I gave everyone to get the wheels turning. And I asked students to sort of visualize the rules of glass materiality and also those things as they relate to like glass science in the real basic ways that we can kind of have access to in our processes and in our engagements with the techniques that we employ from studio to studio. And I asked them to identify the kinds of things that we have been trained to avoid. Next slide. So we have several glass studios in our program that I'm really excited about. And I asked them to kind of think about how this notion of glass wrongness and these rules for what's right versus what's wrong, how do they live in these different places in different ways? Like, where does glass wrongness live in the cold shop? Or where does it live in the kiln shop or in our mold making or in our flame working or in the hot shop? And so what kinds of terms come to mind as we think about the things that we're trying to stay away from? What phrases come to mind? And after we've identified those things, the challenge that I'm kind of posing is now, how can we like go there? How can we lean into those things on purpose and generate an artwork that relies on these sort of things we've been trained to ignore or avoid? Next slide. So I'm the guy that sees this kind of deterioration thing today as kind of rich and full of artistic opportunity. And I look forward to talking more about that with the gang later on today. Next slide. So I'm wanting to use this last chapter to look at ways in which this idea of intentional failure in terms of glass and glass working has been navigated through different professionals in the contemporary field. Next slide. And I'm going to start with myself. So I have 3 artworks that I want to show of myself. I have 3 artworks of other people that kind of help expand my kind of vantage point. But this is not about material failure as much as it is about structural failure. But it's a kind of glass wrongness that's prompted by basic annealing theory and an interest in how objects come undone at annealing temperature ranges that are just known to be too high for the glass bodies that we use and glass objects that we make out of them. Next slide. So this, I guess, a small installation is really just a lowbrow method of documenting the slow collapsing of the structure of this glass object through a repeated exposure to about 850 degrees centigrade for about 15 minutes at a time, many times over, and just wanted to sort of create a time lapse of its collapsing, because we can't necessarily see those things when they're inside of an oven. Next slide. This is another goofy exploration that thinks about deterioration by avoiding that whole annealing process altogether. So one blown object was created on 3 separate occasions. And then when I finished it, I had laid out sheets of paper on the studio floor. And what I did is I would tap this object off onto that paper. I would tap it off the punty, and I would tap it off in a variety of orientations. One was right side up, one was upside down, one was sideways. And as that object kind of rapidly cools down in the sort of real space of the studio, it would freak out, it would stress, it would deconstruct itself. Next slide. So what this experiment was wanting to do was, it was asking a question as to whether this method of deconstruction could be mapped out through burning, by what broken glass parts might fall into the paper and when, based on what heat was still held within them. And I just wanted to know what kind of image might that make. And as you can tell, it didn't really make much of an image after all, but there's a lot of other cool moments that I would love to talk about maybe another time. Next slide. This is an odd research project about deterioration of a hot glass object dropped into a bucket of water behind my bench. And I don't think I would call this an artwork. It might be someday, I'm not sure. But I will say that there was an interest here to witness the immediate energy changes between the glass and the water in a few ways. Next slide. I was mostly interested in this experiment to catalog states of change in this moment. I think, you see video footage being projected here of the hot glass object coming undone in the water. But I also was interested in cataloging through other sort of interesting ways, like through sound files captured of the glass being quenched, or also sound files of the water's sizzle after submersion. I don't know. There's many other sort of like data I've been trying to collect in that sort of moment, but I don't know where it's going, and I don't know how to deal with it yet, but it fits today's topic in its own way. So I thought I'd bring it to your attention. Next slide. And just to kind of wrap that weirdo experiment up, as a side note, I was able to explore that sort of experimental hotshot thing at the CMOG Amphitheater Hot Shop a few years back. So in case you're interested, it is on YouTube. If you give my name a Google, it should pop up. And I should say that if you go for the glass, you'll stay for the narration. Eric Snee and Dr. Jane Cook add an extra level of poetry to talking about what's going on that I thought you all might be interested in. Next slide. I have 3 artist examples from people who aren't me. I want to start with Maria. And this is a kind of deterioration by way of incompatible elements infused within the glass body of these blown glass objects. Next slide. So there's a tension happening. There's a discrepancy between what the glass is wanting to do and what these foreign materials are wanting to do. And so cracks are developing, they're slowly spreading, and the structure may be falling to pieces at some point if it's not already. Next slide. This is a fracture-based, thermal-based kind of exploration of glass's capacity for releasing stress through a very performative sort of method of art making. What you see here are sheets of tempered glass that are set into compression frames, and several folks were given different kinds of hand torches typically used in the hot shop. Next slide, please. And the performance lent way to a fracture and breakage kind of symphony. And so each participant was behind each pane, kind of activating their torch in various ways. And that sort of led to a very, not only spectacular sort of moment of bursting, but also it lent way to a very cool, broad and complicated palette of line and patterning in each of these sort of cases of thermal stress. Next slide. This is the last artist I want to introduce today. This is Renoy, and she's engaging ideas of uncertainty and change over time in her own way. Change as it relates to her doubts and shifts of her identity. And so she created her own specialized glass formula and then cast a very simple phrase in glass lettering, which is I am. Next slide, please. In this case, deterioration is happening at the hands of a wrongness in glass chemistry, and it was done so on purpose. And so this glass is going sour over time, and it's caused by an instability in the chemical composition of her formula, which has been talked about a few times already today. And so this phrase, even though it's kind of saying the same thing in each sort of photographic documentation of it, the phrase is changing, even though it's the same, and it's changing based on the condition of the glass changing. And I thought that was a really wonderful way in which language and identity sort of paralleled with the condition of the glass body itself. Next slide. And that's it. This is where I'll end the intro talk. And these are the places you can find me online if interested. And I look forward to the rest of our discussion today.
Great, David. Thank you. Really inspiring. Thank you for bringing the maker side of things to our discussion today.
My pleasure.
So panelists, given the time, I want to get straight to your questions. So I'm gonna, I think, skip to your all's Q&A, and I'll go last if there happens to be any time. So this is where we're taking a slightly different approach. And in talking with our panelists, I started to wonder what we might be missing in thinking about their work. So what is clear, though, is the common thread throughout all of our work is curiosity. So in the shared spirit of curiosity, we've invited the panelists to create the Q&A section by asking each other questions. So panelists, please take your time answering, and then feel free to go ahead and ask your own question. So if Rob would please start us off with the question for Bodil.
Oh,
Sure.
yeah.
Bodil gets the hot seat.
Yeah.
So I was really fascinated by the way that you cataloged your glasses and that you're beginning to monitor the corrosion over time. And I just wonder if you could have any measurement or any quantification of the corrosion deterioration process, even if it doesn't exist. What information are you looking for, and what do you want to measure as a way of cataloging the corrosion process over time?
Well, for us as a conservator, it's in the word conserve. We want everything to stay the same. So small changes we like to capture, and image is maybe the most how do you say, what's the word, but the best way to capture small changes. But it has been tried with the second survey to make images and try to make the same image, like in very under a microscope. So it's an image where you can really zoom in, so you could really, and we try to it's been tried to sort of have the parameters the same, like the objects is in the same position, which is hard enough because sometimes there's no back or front, it's just a vessel. So we have the same position, we try to have the same lighting, even measure where the lights are, where the camera, etc., etc. And even then it is sort of possible, but to have it exactly the same is really, really hard. So the slightest change in light or makes already a sort of change in the image, and that sort of disturbs if you want to capture a really small change, because then you don't know if it's because of light or so. Getting back to your question, I do think image, but in a way that we don't have, but to have things really next to each other that you can see, like this is moment A and this is moment B, and we see this kind of change. But that's just one part of the whole story, of course, because then we need to act on it. And that's the second question, like what really was the cause of the change? Is this really material? Is it the glass itself that causes it? Or was it something that we did? Did we move it around a lot? Or did we put it in a cabinet with closed doors that maybe was not the best idea because it maybe needs a bit of movement of air or not? So, but getting back to it, I think, yeah, image in a sort of 2.0 version to really capture small changes. That's what we were looking at. And I think that's the best way, because words, you get lost with language. It's really hard. Yeah. So I think that's it. Did it answer your question a bit?
Yeah, it did. And I think with even what Yus was talking about earlier in terms of measurement of degradation products over time, I think coupling the images with an analysis gives you a little bit more information of, what's going on, what the product, what the reaction product is.
Yeah, of course, together with analysis, if you can really sort of swap and measure and you have a quantity, that could also be, of course, very good for us, because then we can say, oh no, it's leaking more, or yay, we're doing great because it's leaking less. But we, yeah. So maybe combination. So image and Guus, we need, yeah.
Thank you.
Yeah, welcome.
Oh, please go ahead with your question for David.
Oh, okay, yeah. Well, I don't know if my question is really fit, but it's more philosophical, because what makes a failure a failure? If failure is not seen after the making process, but it is within the object and only be seen after 10 years, or it's seen because the circumstances the object has been was not fit for it, and it's changes, is still a failure to in your field.
Yeah, I feel like I have a lot of thoughts, and I'm trying to chase one down so I can be a little as coherent as possible, which is not a strong suit of mine. I fail at it, as a matter of fact. One of the thoughts I had, my first take, is that of all of my sort of knee-jerk reactions, I don't really have a one-size-fits-all sort of way to answer that question. But what makes a failure, I think, is defined by maybe something that has to do with, and it's subjective, depending on who we're talking about and what that person is doing and what that thing did or did not do. I feel like I think how I define failure is perhaps something that perhaps falls short of whatever our personal expectations were for whatever it was that we're pursuing, and kind of when reality kind of presents a different scenario than what our vision was. I think that's kind of, maybe in a nutshell, the only sort of clear way that I can maybe start to think about that in a public way.
Yes. So if that's the approach, then maybe the museum collection with all these degradation problems are all, we thought it was stable, but it's not. So they're all our little treasured failures.
Yeah. And so the back end of that question, I think, is also kind of cool, because it presents two different thoughts about when things kind of go wrong down the line. And one of those things is like, is it still a failure? Perhaps, but I would follow that up with, like, is it fixable, or is it not? Is it something that can be salvaged? Or is it ruined in like the ultimate sense, like it's just toast, it's done? But then the poetic side of David comes in and then says, but is that cool? So, it doesn't really kind of tick all the boxes of logic and practicality, but that's kind of the game I play. I have the liberty of, like, not having to worry. I mean, I should, and I do, but I don't have to worry about it in the way that I think scientists, or at least conservators, have to.
No, you can accept, and
I might make use of it.
Yeah. Okay. Yeah. Okay. Thank you.
Yeah. Great questions.
Yeah.
I have, yeah, along those lines, Koos, I have something that I'd like to ask you. And you know who you're dealing with now. It's just an artist weirdo. And so I'm thinking about the things that you were talking about today. And I have watched other presentations that you've given. And so I really like your approach to glass deterioration as it relates to historical glass objects. And I guess I'm wondering if that research has sort of lent way to anything that you thought would have been interesting or useful to tell folks like me, people who are contemporary glass artists in the now.
I think many things. It depends a little bit on what your goal is, but it really triggered me into going back to every glass collection I visited and trying to figure out what I've seen there. And there are a lot of things which I didn't expect, but if you start looking closer into these historic glasses, which have aged for centuries sometimes, then you see all these very peculiar, and they are not as dramatic as your work, I think. So they're all very not as extreme. And I really like what you showed, because it's all, I think it's a scientific experiment as well, what you're doing. And you're documenting everything that's happening to the material, which I think is pretty unique. Not a lot of people do that when they are making glass. But what I've seen, for example, is sort of the gradient, non-homogeneous degradation of the material. So, for example, when you have a wine glass that is stored in a wooden cabinet, the foot degrades quicker than the main body of the chalice, and that's either because, when I'm thinking about glass degradation, I'm thinking about composition and environment. But maybe over the last 2 or 3 years, I've added a third component, which is stress in the material. So that relates to the production process. So how is the glass produced? Is it bent? Is it folded over itself? What's the place in the annealing oven? Does that influence the properties? And I think as an artist, you could probably make use of that. And I've seen, I think there is an effect in the way the glass is blown. So I've seen you remember the manganese discoloration? I've seen that occur not homogeneously across an object, but in spirals up or down. And I guess it has to do with the way it was made. So if it was twisted quick enough, or if there's an inhomogeneity in the glass batch. So I guess these are all things that happen on a long time scale. So you would have to be patient if you want to take advantage of that.
Become immortal.
Yeah. And one of the things that I thought about was also triggered by Rob's presentation is the bioglass. I don't know if you can incorporate that in your work, but if you can deliver either something that's corrosive to the inside of a closed vessel using some bioglass, there must be something artistic in there as well. Is that helpful?
It is. In fact, when I was watching Rob's, actually, when I was watching all of you, I thought of various students that I'm working with who I might direct things that you had brought up that actually fits really well into where we're going this semester, and this talking about how to implement failure in very cool conceptual ways. So Rob, yeah, those things definitely. Bodil, definitely. You, Koos, definitely. So I'm so glad that I hope my students are out there watching this right now. And if they're not, we're going to watch it together in class soon.
Nice.
Thank you, Koos.
Yeah, thank you as well. So my final question was to Rob, to go full circle. And what triggered me is that we are looking at glass degradation on completely different time scales with completely different applications. So therefore, the way we look at the alteration of the material is different. But it must be an important factor in your design, in your patents. How will the material behave over time? And relating to my own research on identifying unstable glass objects before changes occur, I was wondering, in what state of the production process do you notice degradation, and how does it affect the design of the glass, and to what extent can you control it, or is there always an uncertainty factor? And it also relates a bit to the cost, I think, you have for the production. Oh,
That's a big question.
yeah.
You know, certainly we, for applications like a bioactive glass or for a pharmaceutical container, we think about what are all the long-term mechanisms that are occurring, and what is our customer, or what is the end user really wanting out of it. And we try to build as much of that into the design phase as we can. And it may mean that we go through many iterations, either on composition or on prototypes, in order to see if we've accurately understood the mechanism and if we've addressed it in the right way. One of the reasons why scientists will engage, or commercial folks will engage with the art community, is that you and through your museum curators, you have access to glass articles that have been stored for thousands of years. So if I'm interested in how a glass is going to degrade in more than 3 years, I can work with you to say, well, how did it corrode over 1,000 years? And that will build strength in our models. So yeah, we do engage on that failure process very early on in our design phase, but then we will run both accelerated and non-accelerated studies so that we make sure that we are bracketing the response in the right way. And it's fun because we go over the full spectrum, right? From glasses that are corroding in minutes and weeks to ones that are taking years and decades to degrade. So it's been a lot of fun to learn and to see the variety of corrosion responses we can have. And I'm still looking for ways of taking advantage of some of the artifacts that are seen. My favorite is the layering that occurs on the outside of containers that have been stored under salt water for a long period of time, where there can be dozens or hundreds of layers. There's something there commercially, and I just don't know what it is yet. So it's a really interesting intersection of art and science. Does that answer your question, Yus?
Yes.
Thank you all. In our last 1 or 2 minutes, I'm going to thank our panelists. We're so grateful you agreed to join us in this really unique exploration. And thank you to the audience for joining us from wherever in the world you are. And a huge, huge thank you to our colleagues running seminar. Thanks for all the work that you're doing behind the scenes to make this possible. So with that, please find me and Astrid and any of the panelists who wish to pop in one of the community rooms, which you can enter through the lobby. Otherwise, we'll hope to see you at the next talk, which will be at 1 p.m. Eastern Standard Time. Thank you, everyone.